Let's do some more evaluations of the nth term of a limit, or nth term of a sequence. We're going to start off doing a sub n equals natural log of n squared over 3n. Now, if we look at this directly and we just say, all right, what happens as n goes to infinity, just naively? N squared, excuse me, let me write something here. This is going to be Cn while I'm looking at it. If I plug in infinity here, I get sort of an infinity on top and an infinity on bottom, which is, not exactly super helpful or fun. What I'm going to do real quickly is I'm going to rewrite that as 2 natural log n over 3n. And that'll help us out a little bit. It still doesn't solve our problem. We still get an infinity over infinity. So what I want to do with this limit is I want to apply L'Hopital's rule. Let's say the limit as this goes to infinity is equal to the limit of the derivative of the top divided by the derivative of the bottom. So I end up with the limit as n goes to infinity of 2 over n over 3, which is 2 over 3n. With that limit there. Sorry, my handwriting's pretty terrible. But if you look at this, you say, okay, well, as n goes to infinity, that thing gets really large on bottom, so it shrinks to 0. Pretty simple, right? Not a problem. This one's also a little more interesting because we've mostly been dealing with things that are kind of in like these fractions, but I have this 4 to the 1 over n. So what I might do is I might, plot this, right? I might say the first term is 4 to the first power, which is 4. It's, if I do the second power, 4 to the 1/2, that's the square root of 4, so that's 2. And then it becomes a third root, and the fourth root, and the fifth root, and the sixth root. And if you plot those, it kind of shrinks down. And you'll see it kind of move towards a specific line. And let's see if we can't figure this out. So what we want to do is kind of directly plug in infinity. We can't really do that, but for practical purposes, if we use like a 1 over infinity. Well, 1 over a really large number is basically 0. And as long as this number isn't 0, you're pretty okay. If this number is 0, it gets really, really nasty really, really quickly. And I wouldn't recommend that, but in this particular case, it's fine. So the answer is also 1, right? Not a problem. What you find is this is a really important sequence because what it shows is if you start taking this square root, cube root, the fourth root, fifth root, it starts to crush the number. It just starts to crush it down to 1. So if you keep applying roots, it just crushes the number down to 1 eventually. And that's kind of an important result because it helps you understand the nature of how these functions work together and play with numbers. But anyway, I digress. Let's take a look at this one. Cosine of 5n over 2 to the n. Now this is a problematic sequence, specifically because cosine of 5n, it doesn't have that periodic behavior because it's not like 5n pi. If it was 5n pi, it'd be like you'd end up with 0 and -1 and 0 and -1, and it would just, and +1, it would just oscillate between 0, 1, and -1 in like a 4 cycle. But we're not doing that here. We have some number that's just oscillating. But what we have on bottom is 2 to the n. Now 2 to the n gets really big really quickly, right? If n is 10, 2 to the 10 is 1024, right? So I'm already at 1,000 by the time I'm at my 10th iteration. If I take that out to, my 20th iteration, I'm already at like 1,000,000. So I'm getting huge on bottom. So how do I show what's going to happen here? Because I don't have it going directly down. So what I can do is I can actually exploit these two properties. So what I'm going to do is I'm going to define two terms. I'm going to say I'm going to say I'm going to say dn is just 0. That sequence is always 0. Doesn't matter what it is, it's always 0. It's a really nice sequence to deal with. And I'm going to define E of n as 1 over 2 to the n. Now, if you think about it, one thing that's neat is that cosine, even though it can be negative, or it can be 0, or it can be positive, it's never going to be larger than 1, and it's never going to be less than negative 1. So, if you think about that, this has to be true, because the absolute value of Cn, of the nth term there, is just the absolute value of the top divided by the absolute value of the bottom. And that's just the magnitude. That's essentially a bound on how big it can get. Well, the cosine function never gets bigger than 1 and never gets less than negative 1. So the magnitude is always less than or equal to 1. And 2 to the n, well, that's always positive. 2 to a power is always a positive number. So this isn't even really necessary. And that's true. So why is this important? Well, this is important because now I can take a look at this limit here of this sequence. I can say, all right, well, what's the limit as n goes to infinity of 1 over 2 to the n? Well, that's, 2 to a huge number, which is 1 over a huge number, or so 1 over 2 to the huge number is 1 over a huge number, which is 0. So I know that the limit as n goes to infinity of dn is 0, because it's always 0. Of course its limit is 0. It's never not 0. And I know that the limit of en is also 0 because we just figured it out. And I know that this holds. So by the squeeze theorem, these two imply that this is 0 by the squeeze theorem. And since this is 0, then by this property, that's 0. Now, look, I get it. It's probably overkill. You're probably thinking, why do we have to work this hard for this? And the answer is technically because that's what's required. A lot of times you can kind of shorthand it. You go, oh, look, that's clearly going to drop down to 0. And this thing's bounded, so I can just, it's just going to drop to 0. I get it. You plot this thing, it's going to go, and it's going to kind of ripple across 0 really quickly. It's just going to look like noise. But if you're really wanting to prove it and justify it and do it the hard mathematical way, you've got to apply these types of theorems.